The discovery was made using LIGO, the Europe-based Virgo detector, and some 70 ground and space-based observatories. Neutron stars are the smallest, densest stars known. A teaspoon's worth weighs 1 billion tons, and form when massive stars collapse and explode as supernovae. Gravity's grip on the star's core during the collapse crushes all the electrons and protons of the various elements there into pure neutrons squeezed into a white-hot sphere just 12.5 miles across. Since 2 neutron stars were involved, the pair was likely a binary, a double star, each of which evolved into a neutron star in close orbit about the other. How they could survive dual supernova explosions and neither be ejected is testament to gravity's might. As far back as 1915, in his general theory of relativity, Einstein predicted that massive objects accelerating around each other would lose energy in the form of gravitational waves. This would cause them to orbit ever more closely over time until neither could resist the gravity of the other, ultimately merging into one. On August 17, 2 neutron stars in the galaxy NGC 4993 and Hydra spiraled together and emitted gravitational waves that LIGO detected as a loud chirp for about 100 seconds. At the same time, they produced a powerful barrage of gamma rays seen by Earth-orbiting telescopes about 2 seconds after the gravitational waves. In the days and weeks following the smash-up, other forms of light, including X-ray, ultraviolet, optical, infrared, and radio waves were seen in the afterglow. Spacetime is the union of the 3 familiar dimensions with time to create a 4-dimensional world. Everything exists in spacetime. Massive objects like the Earth and Sun bend or warp spacetime in 4 dimensions, much like a bowling ball placed on a trampoline creates a dimple or depression in 3. Gravitational waves ripple the fabric of spacetime like a wave lifts and lowers water. In other words, it briefly shifts an object's position. Not by much, mind you. LIGO's detectors are designed to detect a shift of 110,000th the wide of a single proton during the merger, and seen in the video, a plume of dust rich with newly formed heavy elements including gold, silver and platinum was shot into space and seen by the US Gemini Observatory, the European Very Large Telescope, and the Hubble Space Telescope. Astronomers couldn't have been happier, since the question of exactly how these heavy elements form has been a vexing one for decades. From informing detailed models of the inner workings of neutron stars and the emissions they produce, to more fundamental physics such as general relativity, this event is just so rich. It is a gift that will keep on giving, said David Shoemaker, spokesperson for the LIGO scientific collaboration. The gravitational signal, named GW170817, was detected by 2 identical LIGO detectors in Hanford, Washington and Livingston, Louisiana on August 17 at 8:41 a.m. Eastern Time. At nearly the same time, the gamma-ray burst monitor on NASA's orbiting Fermi Space Telescope had detected a burst of gamma rays. This was not a chance coincidence. Observatories around the world were quickly alerted to the event and gathered photos and spectra spreading the light into a rainbow of colors to look for signatures of elements present of the afterglow as it faded from bright blue to red in the coming days. LIGO detects these submicroscopic blips in spacetime by monitoring the distance between 2 mirrors using lasers. Normally, the lasers arrive at the same point in the exact same time after being reflected from the mirrors, but if something big rocks spacetime, their arrival times will vary ever so slightly. There was a delay of 1.7 seconds between the ripple detection and when the gamma rays were picked up by satellite because the jet takes that long to produce the radiation. Both gravitational waves and all forms of light, gamma rays, X-rays, visible, etc., travel at the speed of light.